Hey there, my name is Devin Goodspeed, and I am an undergraduate in the Mechanical Engineering Department at the University of Tennessee, as well as an obsessive tinkerer with way too many tools. But one tool I do not have is something to remove this fastener to service a scuba tank valve. All right, so I'm just going to go ahead and interrupt myself right there and just give you a little bit of background as far as the intent of this design project. I am, in addition to an engineering student, I'm also a dive master with the University of Tennessee scuba program. And this is a tank valve. Right here is the fastener in question. And they do make a proprietary tool to remove that fastener, which looks like this. And this is one in service along with the parts that go along with it. But these tools are typically manufactured to a very light duty specification. And because our scuba tanks see about 90% of their service life in a pool, which is with the chlorine and everything, it's a mildly caustic environment. These particular fasteners can get stuck and overload the tool, essentially. So what we're attempting to do is we're going to manufacture a tool that has a much higher factor of safety on it, i.e. it's overbuilt for the manufacturer's specifications if we can, and will hopefully have a much longer service life. So what we're going to do in this video is we're going to talk about some design considerations. We're going to go through the calculations for our design. We're going to iterate that design. We'll talk about material properties, environmental considerations that might have an effect on those material properties. And after all of that is said and done, we're going to machine a prototype of that tool in here and hopefully put it to use. So stay tuned. All right, so let's get started. The first thing we need to do is we're going to have to measure the fastener to identify all of our geometric constraints. This is a countersunk fastener, so that needs to be taken into consideration because you can design the strongest tool ever, but it just won't do you any good if it won't fit. So after we write down all of our measurements, we'll use those to both iterate our design as well as calculate deflection due to twist. Okay, let's look at a design iteration really quick. This is our first design, and while this would work, it involves two parts in the bill of materials. It's a bit longer, so material cost is going to be higher. So this wasn't the final design that we went with, but what we can do with this is we can use the tip design to go ahead and calculate deflection due to twist and start selecting our material. Okay, so what parts of this are we going to be concerned about? We're not really worried about the body deflecting just because it has such a high cross-sectional area, so I'm mainly going to focus on the tip of the thing since it's so much smaller. Now, I'm going to use the geometry of the tip when I do my deflection due to twist equations, and what I'm going to do is I'm going to create a composite of these two areas, subtracting the middle for the polar moment of inertia. And I'm going to aim for around 1 degree of twist. That seems to be the best value that I can find. After that, I'm going to do stress in a cantilevered beam with a single point load using the outermost area of the tip itself as the beam, and just kind of go from there because I know that the twist is only going to take into account the shear modulus, and the cantilever beam will also take into account the tensile strength. Something else to note real quick is that the reason why these fillets are here is actually to reduce the stress concentration. If that was just a flat wall, then the stress would be increased quite a bit. Okay, so where do we get our torque values for our calculations? Luckily, the good folks at the Department of Defense have put together this document that basically just defines everything involved with human engineering as far as how hard it should be to open a drawer or anything like that. So they define a low torque value as being 10 foot-pounds. Alternatively, the folks at Marquette University put together this document where they did a bit of research on the amount of forearm torque that could actually be applied with a Phillips head, flathead screwdriver, and so on. And they found the max torque that could be applied with a flathead screwdriver was around 5 Newton meters, which is in the ballpark of about 4 foot-pounds. So I put together a MATLAB script, and what you'll notice is that the shear modulus is 192 ksi, which is essentially nothing for steel, but the max stress is 175 ksi, which is going to rule out a lot of the materials in our Excel spreadsheet. I spent some time on the internet researching and figured out what tool steels were typically used for hand tooling. And what you'll notice is that a lot of these are ruled out from the get-go by the numbers that we just calculated. So we're basically left with D2 and 440A. When we look at D2, the chromium content is decent. It does have some nickel added to it. But when we look at 440A, it has quite a bit more chromium, which is going to add to stain resistance, and that's what we're going to go with. So where are we in our design process? We measured our geometric constraints. We did our initial design work. We researched torque values. We calculated shear modulus and max stress. And we chose a material based off of those numbers. So now what we're going to do is we're going to iterate our design. Our design wasn't bad by any means, but it had 2 parts, and we're going to try and limit that to 1. We're also going to try and limit the amount of material used in that design. So another thing that I'd like to consider is that some tank valves of other manufacturers use a 10 millimeter hex fastener instead of the proprietary fastener that we're designing this tool for. So what I'd like to do is I'd like our tool to utilize a 10 millimeter hex as the drive mechanism, because I think that that would add to the usefulness of the tool and reduce our cost significantly. Here's the final iteration of our design. You'll notice that it's quite a bit shorter, and it does have that 10 millimeter hex on the back of it. These 2 things will help to reduce the material cost as well as the bill of materials. So the last thing I'm going to do in SOLIDWORKS is I'm going to define a custom material as 440A, since it's not built into SOLIDWORKS typically. And then I'm going to fix the ends of the tool and add a torque to the hex drive end. And we're going to model the stress of it. The main reason why we're doing this in SOLIDWORKS is because it's going to take the complex geometry into account, whereas our calculations did not. So the big thing I'm going to look for is the factor of safety, which here shows that it's 4.5. That all looks good. So we're going to go ahead and create a drawing based off of this and then get to producing the tool. Okay, so we've done all of our calculations. We've iterated our design. We've chosen our material. Now we're ready to actually cut some chips and prototype the tool. So I've got a piece of 440 stainless right here, and what I'm going to do is I'm going to toss it in the lathe, go ahead and cut the outside diameter of it, bore a hole in the center to clear the stud in the middle of the fastener, and then I'm going to toss it in my bandsaw, cut it off, and we're going to get to machining. Alright, so here we are using a GO602 Grizzly lathe, which is kind of a benchtop lathe, with carbide tooling at around 1,000 RPM to just size the outside diameter of the part. I should mention that this wouldn't necessarily be required in a manufacturing sense, because you could just order material that has the correct outside diameter if your design was right. Being as that this is a prototype, we're just using what we had on hand. After the outside diameter was turned, we went ahead and used a carbide center drill to spot drill the center of the material, and then followed that up with a number 8 high-speed steel Hertel drill at around 560 RPM to establish the counter bore in the center of our tool prior to machining the actual tips. The next part of this process is that we're going to go ahead and cut off all of the excess material that we left on as work holding in the turning operation. I don't actually have a model number or even a manufacturer for this particular bandsaw because it came to me in need of some repair work secondhand. So around the shop we just call it Steve, and we're just going to leave it at that. The work was then loaded into a collet block, which was mounted in a machining vise in our Excello 602 milling machine. You'll notice that we're using the side of the end mill instead of the face of the end mill. This will help us establish the radius that we had defined to reduce the stress concentrations. And the collet block gives us the ability to machine one side, then flip the whole part over 180 degrees and machine the other side where they will match. For this operation, we're also using a carbide 1/2 inch end mill at around 1,000 RPM. And here's what the part looks like after that machining operation. You'll notice that the tips are left long and then they'll be machined back later. The workpiece was then reversed in the collet block and the 10mm hex could be machined. We did this simply by machining one face, indexing the hex over to the next flat, machining the next face, and so on until we had established the hexagonal pattern all the way around the workpiece that matched the angles on the collet block itself. And here we have the final part, all deburred, polished, all of the hard edges broken over, everything like that. And just a quick check to make sure it does fit inside a 10mm socket. the fit is nice and snug but easily removed, and just to make sure it does fit the fastener. And it all looks good there as well. Alright, so we've got our part machined, it's looking good, it fits, it's deburred, it's polished, everything's nice and shiny. The only problem is that it won't work as a tool. And the reason for that is it's too soft. It's annealed material right now, so what we need to do is we need to bring some martensite back into it. We need to harden it. So this specific material for the heat treating schedule requires a heat soak at 1400 degrees and then heat it up to around 1800 before you quench in either warm oil, or you can do what's called an air quench. We're going to quench it in warm oil today. So I have a few ways that I could heat up that that material to heat treat it. One way is we could use this kiln here. There's also a set of oxyacetylene torches back there. Each one of those methods is effective, but they're also big, bulky. That kiln takes about 6 hours to heat up. For such a small part, it's just not practical. Excuse me. So what we're going to do is we're going to use just a simple propane torch from a hardware store. They heat up to their temperatures around 3600 degrees. Should be fine for what we're doing. So I'm going to mount it in this vise here, stand up the propane torch, and just let it heat soak for a while before we actually quench. So let's get to quenching. While that's heating up, I'll go ahead and explain what we're trying to do here. So this is an iron-carbon phase diagram. You might remember this from MSE 201. We have about 0.75% carbon. So what we're looking for is we're going to ramp the temperature up to around 1400 degrees Fahrenheit, let it heat soak there. Then we're going to increase the temperature to 1800 degrees Fahrenheit to really get firmly into that gamma zone, that austenitic zone, and then quench it to lock that grain structure in place. Now, how we're going to measure that temperature is by the chart on the right, which is a visual means because most laser thermometers only go up to 1500 degrees. Now, keep in mind that the camera will adjust its exposure, so the color might not reproduce exactly correctly, but trust me, it looked right in person. And here we are going for the quench. So one thing to notice that this is warm oil. It's Parks 50 oil in that bucket there. And something else, guys, don't be stupid like me and actually use a respirator. You don't want to breathe this stuff in. Alright, and a quick little test to see if the heat treat actually took is if it skates a file. If you listen to that sound and it's not digging in at all, then that's a good evidence that it did harden up nicely. And here we are back at the workbench. One thing to note is that whenever you heat treat something, the dimensions will change slightly, so it's always a good idea to double check everything after heat treat. And here all I'm doing is I'm just putting it through its paces, make sure that the tool works correctly. This tank valve manufacturer actually didn't give us a torque spec for what this fastener should be tightened to, so that's why we went with the Department of Defense standard. And everything worked just as intended, both in disassembly and reassembly, so this tool is ready to be put into service. All right, we made our calculations. We talked about some design considerations. We iterated our design. We talked about some material properties. We chose a material. We discussed some environmental considerations. And finally, we made the dang tool. So that's typically what goes on whenever you're talking about prototyping a tool. So the next step would be to actually put it in service and get some feedback from the end users, see if there's anything you need to change as far as ergonomics or anything like that, and kind of iterate your design that way. But I appreciate you guys staying on board with me during this process, and thanks for watching.